Okay, so what do we need to do next? We got our strain. From our strain, we get our stress. So the step 3 is very simple. What is the relationship between strain and stress? Oh, I already did it over there. Now, of course, gamma is a function of x and y. So all what I need to write is that tau of x and r is equal to gamma of x and r times the shear modulus. Now, the shear modulus does not need to be constant anymore because I'm graduating to advanced torsion. Okay, so I'm graduating to advanced torsion, so my shear modulus can change from layer to layer. You know, this guy can be made of cheddar cheese, and this layer can be made of steel, and this layer can be made of pastrami. Okay, and it's a delicious shaft, fantastic shaft. The assumption is that as I twist this thing, they all come along for the ride, okay? But I may have different moduli in my little composite shaft.
Are you using little r in terms of like any r, or?
Oh, this one here means the tau. Sorry, let me make a drawing of this, so that maybe is going to help you. So let's do gamma first. Gamma is linear with r. So the shear strain, so the strain, if I draw my shaft like that, and on top of the shaft, so that I can use the axis as a function of r, I draw gamma, okay? My gamma is going to always look like this, linear. So the gamma is always linear with r. The biggest gamma is always going to be at the outer radius r, okay? The gamma, linear with r, no problem whatsoever, is just given by that expression. You see, at r equals 0, how much strain do I have? 0. At the center of the shaft, I don't even know what's going on around me. There is no strain at the center of the shaft. It's like the eye of the storm. Don't see anything.
There's no strain? Oh,
at the very center of the shaft, where r is equal to 0, on that line, there is no shear strain. Because if I'm at the center, I really do not know which way should I strain, right? The shaft is axisymmetric. So at the r equals 0, I have no strain. And then as I move away from the center, I get more and more strained, like the winds in the hurricane. Nothing at the center, bigger as you go around, okay? Now, stress, let's make a first simple case. Let's say that I have a shaft that is homogeneous with, so this is a homogeneous shaft with shear modulus G. Okay, if everything is made of the same material, now I do the same thing and I plot tau of x and r, this is x, of course, as a function of r. Well, guess what? In that case, because G is uniform everywhere, I'm just going to take this plot and multiply by a constant G. So if the shaft is homogeneous, my tau at every point in the shaft is going to be given by the same equation. So this slope here is G d phi dx, if I only have one G, right? Because tau is G d phi dx times r. So if I plot as a function of r, the slope is G d phi dx. Good? Now what happens if I have a composite shaft? Let's say first I make a shaft which has a shell which is softer than the core. It's a soft shell shaft, like the crabs in Alaska? I don't know. So the core is very, very hard, and the shell of the shaft is soft. So in this case, I have G of the core bigger than the G of the shell. Okay, I have a soft shell. At least I have a soft shell compared to the core. Okay, so in this case, what I get is that when I plot tau as a function of x and r, when I am inside the core, this gamma inside the core gets multiplied by G very big, a big G. So inside the core, I get a very steep tau, like that. If I move outside of the core, now the same function, this part here, is going to be multiplied by something small. So my tau is going to jump. And now on this part here is going to look like that. The slope here is G of the shell times d phi dx. The slope here is G of the core times d phi dx. If I want equations, I can write that the tau of the core is equal to G of the core times r d phi dx, and that the tau in the shell is equal to the G of the shell times r d phi dx. Of course, the r for the shell in this case goes from here to here. The r of the core goes from here to here. So see, this equation here tells me what tau is at every radius on that x cross-section. If I was at a different cross-section, I would have a different gamma, so I will have a different tau. But this equation here tells me what tau is as a function of where I am. And that's why G is also a function of x and r. The G can be different here from here to here. If I had the opposite kind of case in which I had a core that was softy, and I had a very hard shell, so in this case, the shell is hard and the core is soft. So in this case, I have G of the shell greater than G of the core. Then when I plot my tau, I will have in the core, I will have a small slope because my G is small. But as soon as I hit the hard shell, I'm going to be on a different slope. You see? Because I jump from something that can go along to gamma pretty nicely without complaining much to something that says, wait, this is like a lot of effort for me to give you this shear strain. You better give me a lot of stress to make me do that. Okay, so my plot goes up. Notice that all the lines go towards 0 because it's still linear with gamma is still linear with r. Okay? And so I got my shear stress distribution on the cross-section by taking my gamma of r and x, which is r d phi dx, and I multiply by the G of the spot where I want the stress. Okay? Almost there, I promise you. We're almost there. So the only thing that I need to do now, are we okay? Can you stay with me for another board? One more board. And then we're going to put it all together, okay? Stay with me? Yes. Okay. Okay. 1, 2, 3, 4. What is missing to our story? What is the thing that I've still not done? What do you think? Torque resultant. Absolutely on top of things you are. Okay, so let me keep this job here because this job is still good. I don't need to get rid of that. So the picture that we need for the torque resultant is still the same picture. So we want to know what is the torque resultant on our leg. So this is step number 4. what is the connection between the shear stress and the torque resultant that comes out of this section. So this is the torque of X. Where does the torque come from? It comes from all the shear stresses that are in this layer of delicious leak. Okay, now, when I draw the shear stresses, you see I make them smaller towards the center, because now we know that the shear stresses are smaller towards the center and bigger on the outside. I cannot just say that the torque is tau times the area, because tau is not constant over the cross-section. I got to do my integration. There's no way around it. How do we do my integration? I do the same thing. I take a little layer, like I have here, and I notice that on this layer, because I'm at distance r, I'm going to have on top of this layer, like that, all around this layer, I'm going to have a shear stress, which is tau of x and r. How much is tau of x and r? I'll just tell you up here what is tau of x and r. This is equal to r times d phi dx times g of x and r. We just did it up there, right? So if I have a thin shell of thickness dr, and with shear stress tau, what is my torque resultant? There it is. I already did the job. I'm not going to do the job again, right? So this thing is something that tells me if I had this tau on something of radius big R of thickness t, this is the torque I would get. Well, guess what? I know what my tau is. My radius is more r, and my thickness instead of t is dr. But I can still use the same result as that one. 2 pi r squared tau r tau equal to 2. So this thing is 2 pi small r squared tau of x and r, which is this thing here, r d phi dx. Actually, let me write it as tau of x and r, otherwise it's going to be too much space. Tau of x and r, 2 pi r squared tau of x and r times the thickness. The thickness is dr. Okay, so this is the torque that this layer here of the shaft is giving me. Because the thickness is only dr, this is a d torque. It's a little tiny itsy bitsy differential torque. So out of this shell, because this one is dr, comes a little torque dt. So this thing is a small differential torque, dt. You see? We good? Well, guess what? I'm going to just get the total torque at x by integrating over the area all the contribution of each layers. I take this layer, I sum it up. This layer, I sum it up. This layer, I sum it up. And I get that the whole torque is going to be the integral from 0 to big R of 2 pi r squared. My tau of x and r is r d phi dx times g of x and r times dr. This is my torque resultant. It looks ugly, but it's not that ugly. Okay? Why is it not that ugly? I'll show you why it's not that ugly.